Example, if resonance is pushing a swing each time, so alpha has high ionizing power and low penetration, okay, and the gamma has low ionization and high penetration, and this is because alpha is charged and massive, so it makes more collision inside matter, and it comes to stop uh, in a short distance, while gamma has no charge and no mass, so it penetrates more in material, but at the same time it ionizes less. Okay, damping is in opposite direction to uh, velocity. Okay, it cannot be an opposite direction to acceleration because acceleration is opposite in direction to uh, velocity. So we need damping to be opposite to velocity. Why it cannot be in same direction of acceleration if acceleration is opposite to velocity and damping is opposite to velocity? This is because if it is in direction of acceleration, amplitude will increase, and to make damping is to make the system stops, so velocity comes to zero, and certainly amplitude also comes to zero. So we need to remember that inverse of Hubble constant is the age of the universe, and for this we expect 1.37 times 10 to 10 to be in the denominator. Okay, so we expect C or D. Okay, and certainly not A because we have also the conversion from year to second. So it is only C, sorry, it's not D at all. Okay, this is the damped oscillation because we have the friction with water draws energy from the system, which is the spring with the hand mass. We have here Ix to Iy equal to 4, and we know that I is L over 4 by D squared. So if L is the same for X and Y, and certainly for pi is constant, we mean by that intensity is inversely proportional to distance, and Ix over Iy is same to dy squared over dx squared. So this is 4, and taking square root dy over dx equal to 2. Okay, so dy equal to dx, or dx is dy over 2 or d over 2. Okay, both have same distance and temperature of star B greater than that of Q, STB greater than TQ. We have lambda max B less than lambda max Q. Okay? So we have A and C. We should choose from one of these graphs. The other condition here, as they have same distance. Oh, sorry, we can exclude also the graph A because it is here's the frequency and we have the wavelengths of B less than Q. So the correct answer is only C, and we don't have to think more about anything else. So we have for force G N over R squared, and for potential it is Gn over R. So it is clear that there is inverse proportionality to R, either with square of R or just R. So both of force and potential, even this is potential energy, it is just potential times the mass, can make the adjustment here. Okay. We expect these two quantities to be opposite and increase or decrease to the distance between Earth and star, and this is only applies here. Okay, we have for the balancing, the oscillation of mass connected to spring 2 by square root over of m over k, and ratios will be directly proportional to square root of masses. So it is equal to square root of 2, because this can certainly be written as just 1 square root of m1 over m2, and m1 is 500 and 2 150. So these two answer is C. We have for constant temperature equal kinetic energies. So half m x zero equal to that of R1. So the relation between masses is inversely proportional to that of ns of speeds. Okay, so we have here, if we take square root of both, we'll have that square root of 3 equals square root of ms a over RMS x. Okay. if we want x over a, it is the inverse of this, so it is 1 over root of 3. So we have g equals, oh, sorry, gm over r squared is the mass of the planet, okay? And as the radius is 40% greater, this means that its mass is 1.4 times mass, times radius of Earth. Okay, this is all squared, and the answer, remember, it is meter second minus 2. So we have change in frequency over the frequency equals to V over C. So V equals to this is what we observe, and this is what we observe from the galaxy, and this is what we obtain from the lab. Okay. This difference divided by what we obtain from the lab, which is the F. Times C. Okay, we can simply remove this factor, and this difference, okay, it is so simple to do on calculator. So to scale, we need a kinetic energy to equal the potential energy. Okay, here is the potential, and here is the potential energy. We can eliminate m from both sides. We can rearrange and take square roots. Even if you don't fully understand what the question wants, you have always parts of questions connected to each other. So you most probably will use what you get in the previous part. And as we are talking about sun and Sagittarius, which is a black hole, it is obvious that the capital M here goes for Sagittarius. Okay, so to find the radius, we will just rearrange first by squaring both sides, and second by getting this in the denominator. So we can after that substitute here. And this is times mass of sun. So as we have constant pressure, okay, we can use the Charles formula, T2 over T1 equals V2 over V1. And for this sphere, we have 4 over 3 by R cubed as a formula for volume of a sphere. So we have a direct proportionality between V and R cubed, and T2 over T1 same as R2 cubed over R1 cubed. So we can after that find T2 by simple rearrangement and substitution. Don't forget that temperature in all of such formulas in Kelvin. Okay. And here I know that these numbers are for diameters, but as you may guess, diameter is just radius, sorry, it's just diameter over 2. So division by 2 to the power 3 for numerator goes away with that of denominator. And we just get the T2. This means 88 degrees Celsius, and this differs from the 95, okay, by 8%. Okay, so if we take the difference between the 88 and 95 and divide by 88 or by 95, we have a difference of 7 or 8%, and this is greater than 5%. I may say not equal. You may choose it to be equal for a difference of 10%. You must, as the end state, your conclusion. Is it equal, accurate, or not? Okay. So X here is displacement from equilibrium. And not the state from equilibrium. And the minus sign certainly because resultant force in opposite direction to displacement. Okay. So we have here velocity equals omega A sine omega t. And this is because we started from the maximum displacement down, which means cosine wave for displacement. So for velocity, it is sine. You may add negative if you want, but we want to use the magnitude. And as we are searching for maximum kinetic energy, it means also maximum velocity. So sine omega t is equal to 1. Okay? So we have omega to be 2 pi over periodic time, which is 0.64. Oops. And this is in rad per second or second minus 1. And V max to be equal, I will convert the displacement here to meter, as I want the answer here to be in meter second minus 1. After that, I can get the KE max. It's half. This is in kilogram, is like that, because I want the final answer to be in joule. Okay. Or you can use the relation for the bouncing oscillation M over K. First, you will get K by rearrangement. Okay. You can substitute and get it as 1.73 Newton meter minus 1. Okay. Or kilogram second minus 2. Whatever you want. Here is mass and here is second squared, so this is equivalent to kilogram second minus 2. After getting K, you can get the energy stored in this spring-like motion, okay, of kx squared, and it should give an answer very close to this. Okay, so for acceleration, it is a cosine that starts from the negative direction, and wanted is velocity. We should emphasize here that periodicity should keep the same, because omega is the same, so I can maintain this same periodicity by making kind of lines at both zeros, okay, points where it is 0 and where it is maximum. You can make this by your ruler And after that, for point of maximum, we should have 0, okay? And for point of 0, we should have maximum, but as this start in negative direction, it is opposite to we have displacement here to be cosine, velocity to be minus sine, acceleration to be minus cosine again. So it follows, as both are negative, it follows same order of acceleration. So if we start from negative, we expect the maximum that corresponds to the minimum here. We expect to be in negative also. So I choose here. And for maximum, it is 0. We can make all maximum first zeros. Okay. And here, this is 0. And here is maximum. Here is maximum. Here is 0. And here is maximum. And certainly you can connect them. Oops. In a curve, not sharp lines, and we can end here. Among that it changes color and ET graph.